Now we get to do some multi-step conversions. The question says, convert the following using conversion factors. Let's dive right in. Now, in these questions, you're still trying to boil all this down to two things. One, what are they giving you? And two, what are they asking for? What they're giving you are going to be numbers. But you're going to have two types of numbers. There are going to be numbers that are all by themselves. And then there are going to be numbers that are in a relationship with other numbers. If a number is in a relationship with other numbers, you want to write that as a conversion factor. So let's do this one as an example. You'll see what I mean. This one says the doctor has prescribed 6.2 ounces of a steroid ointment. How many grams of the ointment do you need to request from the pharmacist? Note that there are 16 ounces in 1 pound. So what do they give you in this problem? Where are the numbers? They give you 6.2 ounces. And notice that that number isn't in a relationship with any other number. It just, the question gives it and it's standing on its own. Then, what they're asking for is grams, right? How many grams? That's the unit. But they also give you other numbers. They say that there are 16 ounces in 1 pound. And because there's a relationship between those two numbers, 16 ounces in 1 pound, you write it as a conversion factor. So 16 ounces equals 1 pound. Okay, so this is what we have. These are the puzzle pieces. We have to somehow get from ounces to grams. And right now, using the conversion factor we have, we can only get from ounces to pounds. Now, I don't know a conversion factor to go directly from pounds to grams, but I do have memorized a conversion factor that goes from pounds to kilograms. Okay, let me write that down and see what happens. I know, for example, that there are 2.2 pounds in every 1 kilogram. And then I know I can see a connection between kilograms and grams. I know that there are, in every 1 kilogram, there are 1,000 grams. And so now I have a sort of path of conversion factors. I can use the first conversion factor to get from ounces to pounds, the second one to get from pounds to kilograms, and that third and last one to get from kilograms to grams. So you take the number they gave you that just stood alone, that's 6.2 ounces. You write a multiplication sign, a fraction bar, and the units that you start with go on the bottom so that they'll cancel out. Then you fill that fraction in with your first conversion factor, the only one that has ounces in it. Next to ounces goes 16, going over the fraction bars, like going across the equal sign, and on top you'd have 1 pound. So ounces will cancel, you're left with pounds. But we don't want pounds, we want grams, so we do another conversion. You write a multiplication sign, you write a fraction bar, and the units that you start with here on the top go on the bottom of this next fraction so that they'll cancel out. Now, I'm going to fill this in with a conversion factor. I have 2 conversion factors that have pounds. The one over here on the left, and then this one in the middle. But the one on the left would just bring me right back to ounces, which is not where I want to go. I want to keep getting closer to grams, so I'm going to use the second one here to go from pounds to kilograms. So next to pounds is going to go 2.2, going over the fraction bars, like going across the equal sign, and on top you'll have 1 kilogram. The pounds will cancel. You're left with kilograms. But we don't want kilograms, we want grams. So we do another conversion. You write a multiplication sign, a fraction bar. And the units that you start with, here kilograms, go on the bottoms because you want them to cancel out. Now I'm going to fill this in with my third and last conversion factor. Next to kilograms is going to go 1. Going over the fraction bar is like going across the equal sign, and on top you'll have 1,000 grams. The kilograms cancel, we're left with grams. It's a beautiful day. And now you plug this into a calculator, you would hit 6.2 times 1, enter, divided by 16, enter, times 1, enter, divided by 2.2, enter, times 1,000, enter, divided by 1, enter. That should give you 176.14 grams, and that is what you're going to send to the pharmacist. That's the answer to the question. All right, this question says a patient needs 0.027 grams of ampicillin. The hospital only has 9 milligram tablets available. How many tablets should you administer? Get it right, you save a life. You get it wrong, that patient dies. So first, what does the question give you? It gives you 0.027 grams. And notice that that number isn't in relationship to any other number. That's a number standing all by itself. What are they asking for? They're asking for tablets. How many tablets? But they also give us another number. They give us 9 milligram tablets. Now I know it looks like that number is standing all by itself, but tablets are a tricky and a sneaky and a sly thing. Whenever you have a milligram, a number of milligrams associated with a tablet, it is actually a conversion factor in disguise. Dun, dun, dun. And so you want to relate 9 milligrams. There's 9 milligrams in one tablet. So anytime you have milligrams with tablets, you want to rewrite it as a conversion factor. The number of milligrams equaling 1 tablet. Okay, so these are my puzzle pieces. I have to connect these somehow. Now I can see that if I had milligrams, I could get to tablets. But I don't have milligrams, I only have grams. But maybe I can get from grams to milligrams. I know a conversion factor that relates them. In every 1 gram, there are 1,000 milligrams. And so now I can get from grams to milligrams, from milligrams to tablets, and then I have my answer. So, write the number they give you that stands all by itself, the 0.027 grams. We want to do a conversion. Every time you do a conversion, you write a multiplication sign, you write a fraction bar, and the units you start with always go on the bottom of that fraction so that they'll cancel out. Now I'm going to fill this first fraction in with my first conversion factor. Next to grams goes 1. Going over the fraction bar is like going across the equal sign, and on top you have 1,000 milligrams. The grams cancel. We're left with milligrams, but we don't want milligrams. We want tablets, so we have to do another conversion. Every time you do a conversion, you write a multiplication sign and a fraction bar, and those units that you started with, yep, that's it. Those go on the bottom of the fraction because you want them to cancel out. Now I'm going to fill this second fraction in with my second conversion factor. Next to milligrams is going to go 9, going over the fraction bars like going across that equal sign, and on top you've got 1 tablet. The milligrams cancel. You're left with tablets, and now we're going to get our answer. So you plug this into a calculator, and the way you do it, you put 0.027 multiplied by 1,000, hit enter. Divided by 1, hit enter again. Times 1, hit enter. Divided by 9, hit enter, and that's going to give you 3 tablets. That's your answer. That's how many you give to the patient. The patient lives a prosperous life. This question says a patient's daily need of a sulfa drug is 112 milligrams per kilogram of body weight. How many milligrams of the drug does a 34-pound child need each day? Well, what is the question giving you? Where are their numbers? First, something that's a little more straightforward. The units they're asking for are milligrams of the drug. How many milligrams of the drug? Now, in terms of what they're giving us 2 different numbers. The one number they're giving us that stands all by itself is the 34-pound child. So we're dealing with a 34-pound child, and how much of the drug are we going to give to this kid? The other number they give us looks like it's standing all by itself, but it's not. They have 112 milligrams per kilogram of body weight, and so that seems like the only number there is 112, but actually there's a number in disguise, because when it says there's 112 milligrams per kilogram of body weight, what that really is 112 milligrams per 1 kilogram of body weight. So we can rewrite that as a conversion factor and say that we're going to have 112 milligrams of the drug per every 1 kilogram of, in this case, a child. Alright, so this is what I've extracted from that problem. Now, from here, I can see that if I had kilograms, I could get to milligrams of the drug. If I had kilograms of the child, I could get to milligrams of the drug using this conversion factor. But I don't have kilograms of the child, I have pounds of the child. But maybe there's a way I can get from pounds to kilograms. Ah, there is! In every 2.2 in every 1 kilogram, there are 2.2 pounds. So I have, in every 2.2 pounds, there's 1 kilogram. And I can use this conversion factor to get from pounds to kilograms, and my second one to get from kilograms of the child to milligrams of the drug. So, always start with that number that they give you that's not tied to anything. In this case, it's 34 pounds of the child. Always write a multiplication sign in a fraction bar for conversions, and the units you start with, in this case pounds of child, go on the bottom of that fraction, so that they'll cancel out. Now I'm going to fill that first fraction in with my first conversion factor. Next to pounds goes 2.2. Going over the fraction bars like going across the equal sign, and on top you write 1 kilogram. In this case, 1 kilogram of the child. Pounds of the child cancel. We're left with kilograms of the child, but we want milligrams of the drug, so we have to do another conversion. Every time you do a conversion, you write a multiplication sign in a fraction bar, and the units you start with on top. Here, kilograms of child go on the bottom, so that they'll cancel out. I'm going to fill that second fraction in with my second conversion factor. Next to kilograms of child is going to be 1. Going over the fraction bars like going across the equal sign, and on top of this fraction, you'll have 112 milligrams of the drug. Kilograms of the child are going to cancel, and we'll be left with milligrams of the drug, which is exactly what we want. So you just plug this in a calculator. 34 times 1, then hit enter, divided by 2.2, hit enter, times 112, hit enter, divided by 1, hit enter. You should get 1,731 milligrams of the drug. And that would be your answer for this question. This question, a new question, says a patient needs to be administered 4.0 grams of amoxicillin every 8 hours. If the hospital only carries 650 milligram tablets, how many tablets should you administer each day? So, what are they giving you? Well, first, let's go toward something that's more straightforward. What are they asking for? And here they're asking for tablets. They're saying how many tablets. Now, what are they giving you? And in this case, we're looking for the numbers. Now, I know it doesn't look straightforward because it's not a digit. It's not an Arabic number, numeral. But what they're really asking is, what they're giving you is 1 day. That's the only number in this whole question that isn't tied to anything else. Let me show you why. Another number they give us is 4 grams of amoxicillin. But notice how it's worded. It's 4 grams of amoxicillin every 8 hours. Those two numbers are tied together, the 4 grams and the 8 hours. So we can write that as a conversion factor and say, for every 4 grams of the drug, we're going to have 8 hours. Then consider the other number they give us, the 650 milligrams of tablets. Remember, anytime you have milligrams of tablets, it's a conversion factor in disguise. Here we're going to have 650 milligrams of the drug equaling 1 tablet. There's that many milligrams of the drug in 1 tablet. And so this is the information I've extracted from my problem. And now that we've looked at those other numbers in detail, you can see that the only number they give you that isn't tied to anything else is this each day. In other words, 1 day is what we're working with. Okay, well, looking at these puzzle pieces, I can see that if I had hours, I could get to grams of the drug and maybe work from there. But I don't have hours, I have days. So I need a conversion factor that relates hours and days. Luckily, I know that conversion factor. There's 1 day for every 24 hours. So now I can get from 1 day to 24 hours. I can get from days to hours with my first conversion factor. I can get from hours to grams of the drug with my second conversion factor. But then I'm stuck because this third conversion factor doesn't have grams of the drug. It has milligrams of the drug. But I can get from grams to milligrams because I know that for every 1 gram of the drug, there are 1,000 milligrams. So I can get from this grams of the drug to milligrams of the drug, and I can use this last conversion factor to get from milligrams of the drug to tablets. Okay, now that I've got all my conversion factors, I'm going to take that one number they gave us that wasn't tied to any other numbers, here that 1 day, and I'm going to do a conversion. Every time you do a conversion, you write a multiplication sign, a fraction bar, and the units you start with on top go on the bottom. Here it's days. I'm going to fill that fraction in with my first conversion factor. So next to days is going to go 1. Going over the fraction bars like going across the equal sign, and on top I'm going to write 24 hours. Days cancel out. I'm left with hours, but I don't want hours, I want tablets. So I have to do another conversion. Every time you do a conversion, you write a multiplication sign in a fraction bar, and the units you start with on top go on the bottom because you want them to cancel out. I'm going to fill this second fraction in with my second conversion factor. So next to hours is going to go 8. Going over the fraction bar is like going across the equal sign, and on top I'd write 4 grams of the drug. Hours cancel out, I'm left with grams of the drug, but I don't want grams of the drug, I want tablets, so I have to do another conversion. Every time you do a conversion, you write a multiplication sign and a fraction bar, and the units you start with on top, here grams of the drug, go on the bottom, so that they'll cancel out. I'm going to fill this third fraction in with my third conversion factor. Next to grams of the drug is going to go the number 1. Going over the fraction bars, like going across the equal sign, and on top you'll have 1,000 milligrams of the drug. Grams of the drug cancel, and you're left with milligrams of the drug. But I don't want milligrams of the drug, we want tablets, so we must do yet another conversion. Every time you do a conversion, you write a multiplication sign and a fraction bar, and the units you have on top go on the bottom, so that they'll cancel out. Now, I'm going to fill this final fraction in with my last conversion factor. Next to milligrams of the drug goes 650. Going over the fraction bars like going across the equal sign, and on top you write 1 tablet. The milligrams of the drug cancel out, you're left with tablets, which is exactly what you want. And the way you'd plug a beautiful calculation like this into a calculator is 1 step at a time. You'd hit 1 times 24, enter, divided by 1, enter, times 4, enter, divided by 8, enter, times 1,000, enter, divided by 1, enter, times 1, enter, divided by 650, enter, and you get 18.5 tablets, 18.5 tablets, and that would be your answer. This question says, a subcutaneous under-the-skin injection is given at 5.00 milligrams per kilogram of body weight. How many milligrams should you inject for a 175-pound patient? Alright, so what are they asking for? They're asking for milligrams, and specifically milligrams of the drug. What are they giving you? Well, the number they give you that stands all by itself is 175 pounds. That number isn't being given in relationship to any other number. It's just standing on its own. The other number they give you, 5.00 milligrams per kilogram of body weight, that number is given to you in a relationship. The 5 milligrams of the drug and the per 1 kilogram of body weight. And so we can write that as a conversion factor. We know that there are going to be 5 milligrams of the drug for every 1 kilogram of the patient. And so this is all I can extract out of the question. So I have to find a way to work with these puzzle pieces. Now, I can see that if I had kilograms of the patient, I could get to milligrams of the drug, which is what I want. But I don't have kilograms of the patient, I have pounds. But I know the conversion from pounds to kilograms. It's for every 2.2 pounds of the patient, you'd have 1 kilogram of the patient. So I can use this first conversion to get from pounds to kilograms, and the second conversion to get from kilograms of the patient to milligrams of the drug. So you start out by just writing the number they give you that's not tied to any other number. So here, 175 pounds of the patient. Every time you do a conversion, you write a multiplication sign and a fraction bar, and the units you have on top go on the bottom, so they'll cancel out. Then I'm going to fill this first fraction in with my first conversion factor. So next to pounds of patient is going to go 2.2, going over the fraction bars like going across the equal sign, and on top we'll have 1 kilogram of the patient. Pounds of the patient cancel, we're left with kilograms of the patient, but we don't want kilograms of the patient, we want milligrams of the drug, so we have to do another conversion. Every time you do a conversion, you write a multiplication sign, you write a fraction bar, and the units you start with on top here go on the bottom, so they'll cancel out. Here it's kilograms of the patient. I'm going to fill in this second fraction with my second conversion factor. Next to kilogram of the patient goes the number 1. Going over the fraction bar, well, that's like going across the equal sign, and on top you're going to have 5 milligrams of the drug. kilograms of the patient cancel, and you're left with milligrams of the drug, which is just what we wanted. You plug all this in a calculator. How, you ask? Well, you hit 175 times 1, hit enter, divided by 2.2, enter, times 5, enter, divided by 1, enter. And that should give you 397.7 milligrams of the drug. That is the answer to this question. Thank you so much for your attention.